Yes, there's going to be some, I'm going to tell you right now, there's going to be one simple momentum problem on there. Okay? I'm even going to tell you straight up, it's going to be a California problem.
Thank God.
Okay?
Imagine if it was.
Oh!
I remember how that thing works kind of now.
Shut up.
Here, here.
So, you have a mass of 0.2 kilograms moving along, it hits a stationary mass of 0.3 kilograms that's at rest. Okay? And they're going to hit and they are going to move off together. Okay? I'm going to tell you that straight up. This is exactly how the problem's going to play out. So let's just have a quick review so you all aren't panicked. How do you calculate momentum?
Last time's velocity.
Yeah, so this is just going to be M1 V1 plus M2 V2 equaling. Now, because it's a California problem, what can you do over here?
M1 plus M2 times V prime.
See, was it that bad?
Yes.
Oh, I do remember that.
How do you not remember that?
No, I remember it now. I remember it.
Okay, so the initial velocity,
You could watch it this out. I'll watch it this out.
the initial velocity, the one attached to the spring is going to be at rest. I'm not even going to make it moving. Okay? So then you divide by the combined mass, you're going to find the new velocity. Okay? So, here's your spring. It's going to get collapsed, so it's going to hit, and they're going to move off together. You're going to find that new velocity. So from there, you should be able to say, okay, now, if I gave you like the spring constant, you know, if you said, okay, hey, maybe you could look at it in terms of setting your maximum, God, that thing's annoying, kinetic energy equal to your maximum potential energy. Go from there, okay? So that's going to be the big picture. So I'm telling you, when you're going to get a problem like that, that's how you want to roll this. Now, speaking of old school, okay, so if you wanted to set, if you want to go through and do some fancy math, and you could say, okay, well, my maximum kinetic energy can equal 1/2 Ka squared. So you could set mv squared equal to Ka squared. You could solve for A, you could solve for velocity. There's a whole bunch of different things that you could do with that. So that was just a sample of some things. Let's talk energy, but yet in another form. So,
Another form?
oh yeah, oh no, just old school, okay?
Okay.
Just old school. So, especially for those of you that are new, last problem on the test. This is going to require more writing than my new coming honors physics students are used to. So, what's going to happen? Here's going to be the format of the problem. Is that you're going to be told you're going to have a cart, okay, and it's going to be compressed a certain distance, and then it's going to be let go, okay. Then it's going to roll for a while, and then it's going to come to a stop. So let me kind of model that. Let me flip that over. So you're going to be like this. You're going to push it. It's going to come to a stop. Now, let's go old school. Let's go old school. Energy versus a time graph. Okay? So let's just talk about the kinetic energy first. So if I've got this compressed like that, what would the kinetic energy time graph look like? Anyone but this side of the room. Deacon.
If you're starting in motion?
No, I'm going to start from that perspective to that.
It's going to start from 0 and it's going to start sloping up.
So it's going to start at 0. So this is going to be my kinetic energy line. It's going to start at 0 and it's going to slope up. But then what's it going to do? Or is that all it's going to do?
And then it's going to come back down.
Then it's going to come back down, right? Why?
Friction.
There's friction. If I had flipped that over and done that, then what would my kinetic energy graph do? if it was a perfectly frictionless surface. Then it would just level off. So if it was frictionless, the graph would go like this. Okay? Cool. Let's go old school. So let's go back over like this. So I'm going to make that line up there go away. So let's go back to the idea that there's friction. Okay? When this thing is compressed and let go, this is from the point that it begins to move, okay, away from the wall. The plunger has expanded. Old school is work being done on the cart. Yes. Yes. Is there a force acting over a distance? Yes. Is there a change in the kinetic energy? Yes. What do you know about the work, the relationship between the amount of work done and the change in, oh, they're equal, right? Now, old school, work equals what? Simplest way to calculate work. Simplest way to calculate work. Force times, right? Force times displacement. So, is there work being done to speed up the cart?
Yes.
Is there work being done to slow down the cart?
Yes.
Yes. What's causing the force to make it slow down?
Friction.
Friction. Let's go even older school.
Uh-oh. We're going into the-
How do you calculate mu?
Force friction over force friction. Yeah.
Force friction over
Force normal.
Probably because there's gonna be a.
force normal, right?
Right.
Okay? Right? Remember that?
Yeah.
Okay? So, is there going to be a relationship between the amount of compression that I give to the spring and the distance that the cart travels after I let go?
Yes. Amount of energy in, amount of energy out.
So if I compress the spring more,
You store more energy.
I store more energy,
You do more work.
I'm going to do more work, therefore it should travel
A further distance.
for the distance, right? So let's talk about that energy. So that energy stored in the spring is going to have what form?
1/2
To
K.
calculate it, 1/2
K squared.
kx squared, right? So if I double the distance that it's compressed, what would happen to the amount of energy? It's going to increase by a factor of 4, because it's 1/2 kx squared, right? So, kind of tying this all together.
Oh, sorry. You shouldn't be on the desk.
That's relevant. You see, tying.
I think I understand.
When this begins to slide,
That's scary.
when it begins to slide, is there a net force acting on the cart?
Yes.
Yes. Can I express that as mass times acceleration?
Yeah. If you want to.
I could.
No.
Is force friction what's making the cart slow down?
Yeah.
Yep, Sean? Right? And that equals MA. True? Right? Now, are on a flat surface. What is your force normal going to equal?
MG. I swear he's about to tie something together.
So, what can I cancel out?
Mass.
So this is just going to be a ratio of
How fast it slows down for gravity.
acceleration to my gravitational acceleration. So if I have two objects of unequal mass, but the same coefficient of friction,
Let's slow down.
will they have the same acceleration?
Yes.
Yes. Right? Because the masses cancel out, so it's a ratio of A over G. So, let's play this out. So, let's go back to old school. So, I'm going to compress the spring, and then I'm going to let go of it. So we said the kinetic energy graph was going to start at 0, and it was going to go up, and then it would do what? Then it would go back down. Okay? What would the energy stored in the spring graph do? Would it? Sydney, what do you got?
It's gonna start high, it's gonna go down.
Right?
Yep.
But is it gonna go back up?
No.
Sydney?
No,
Why not?
because it's not being compressed anymore.
Yeah, this isn't oscillating back and forth, okay? This is a one-way trip, okay? So that graph is just gonna start up here and go down like that and stay there, because we're not physically doing anything to recompress the spring, okay? We're not storing it in, going up a hill, it's just gonna be rolling. So this is how this is gonna play out. In this problem, it's gonna say, like, it might say, we're gonna compress the spring a distance of X or variable D or something like that, okay? And then we're gonna say, on the next scenario, it might be compressed to a distance of 3x, okay? So if it was compressed to a distance of 3x, what would happen to the value of us?
Increase by factors.
It would go up by a factor of? 9. So us would go up by a factor of 9 because it's 1/2 k times 3x squared. Okay? Go with that.
Yeah.
Huh? So what would happen to all of those graphs?
They just get
The maxes will be higher.
steeper. Or they get taller and, yeah, they get taller.
They get taller, right?
Yeah.
Because you're gonna have more us, right? And if you start off with more us, you're gonna start off with more kinetic energy, right? So if I compress it further, it's gonna be the same general shape of the graph. But everything's just gonna get amplified because I'm gonna have more us, I'm gonna have more kinetic energy, right? So as it rolls away, if you were to look at all the, this is as it's rolling, okay, this is gonna be an important thing. As it rolls, what are the forces acting on, this is upside down. What are the forces acting on that cart? There's 3 of them.
Force gravity, force friction.
Gravity pulling down, the normal force acting up, and if the cart is going in this direction, force friction is going to be acting in that direction. Okay? Is the force friction going to be doing work?
Yes.
Right?
Right.
Correct.
Is the force friction going to be a constant value, assuming that it has the same coefficient of friction?
Yes.
Right? Because if you look at how mu is calculated, that's force friction over normal. So could I draw, if I wanted to, a force friction graph and then distance? And that distance would be represent the distance that it would roll. Okay? So, let's say that you know the force friction is, I don't know, 5 newtons, and you know that it rolls a half a meter before it stops. So, this you can treat as a rectangle. You can't do that with the spring. Why? You can't draw that type of graph with the spring. Because this is a constant force. With the compression of the spring, that follows Hooke's law. So I can't draw a graph like this on a spring, or I can draw it with the frictional force. Now, if you were to find that area of that graph, what would that represent? Because work is going to equal, in this case, force times distance, right? True? Now, how is that work that's going to be done, and this is where it goes full circle, how is the work that's going to be done going to relate to the initial kinetic energy that it started with?
It has to be the same.
Ah, it has to be the same, because work is going to create a change in the kinetic energy. So again, this is old school, okay? But it's important that you see how things fit together. So work can also, remember, represent a change in energy, okay? Generic ways, change in energy. So in this case, what's the change of energy going to be? What form is that going to be in?
Joule?
Well, no, what form of energy? As it begins to roll, what type of energy is changing? Kinetic. Oh, so that's going to equal the change in the kinetic energy, right? But what was the relationship between the energy that you store in the spring and the energy that you have when it leaves?
It's the same.
They're the same. So that could also equal the change in us.
Whoa.
Whoa. So, which is 1/2 kx squared. So here's the $1 million question. We're going to do some reverse engineering. If I triple that distance that the spring is compressed and make that 3x squared, okay? I'm going to make that 3x squared. What's going to happen to the amount of energy that you have as us? It's going to go up by a factor of 9. So that's going to go up by a factor of 9. So what's going to happen to the amount of kinetic energy available? It's going to go up by a factor of 9. So what's going to happen to the change in energy that's going to happen?
Also by a factor of 9.
So what's going to happen to the amount of work that has to be done?
Also by a factor of 9.
So what's going to happen to the amount of work that has to be done?
That's the same.
9 triples.
Has to go up by a factor of 9.
Yeah. Well,
Basically, adding a coefficient of 9.
yeah. Sorry, it's just you have from delta K, delta E, and then to work, and then you just
Stay
do
with the
another line
transition.
to also
Here's the
work.
recurring theme, factor of 9.
But I guess it's like this.
So what's going to happen to the distance that it's going to travel?
Go up by a factor of 9.
9.
It's going to go by a factor of 9.
Oh, it's
Okay? So this I'm going to tell you, this is going to be the last problem on the test. Okay? It'll take up about a page and a half. I'm going to tell you exactly where the problem's going to be. And this is what you're going to have to articulate, is to be able to look at the impact that it has on a situation. It's going to be a cart, you're going to have a compressed spring, it's going to roll, it's going to begin to slow down. And it's going to say, here's scenario number 1. Scenario number 2, we make a change to the compression of the spring. Maybe we compress it half as much, maybe we compress it twice as much, 3 times, whatever. So the whole key to that problem is going to be understanding that the work that's done is gonna equal the change in the energy. But that change in energy is gonna be the change in us, which is also gonna be the change in the kinetic, okay? So, that's where this problem is going to be. It's going to be the last big problem on the test, okay? And it's just gonna be variables. It's gonna say, hey, this is the distance X, this is the stopping distance. Now, if that flips you out, if you hate that, you can actually make up numbers and say, okay, hey, I wanna have a spring constant of 10, and I wanna have it compress a distance of 0.1 meters. And actually calculate numbers and see how it changes. Or you can just work it purely with mathematics. Typically AP tests, this one is relatively short because it's a relatively short unit. But typically AP tests take longer than honors physics tests do because there's more writing. So for those of you that are new, because that's going to be tomorrow, you're going to have the end of the day, you can just keep working through flex because they're going to let everybody go with flex anyway. But if you need to make arrangements, just understand that if you were a slow test taker and you want some more time, just realize you might not get out of here at 2:40, okay? So, there's that. Okay, let's call it a day. I'm exhausted. I know everybody's south to head out.